Alright, let's take a look at this problem here. We have this circuit, and it says for this circuit find it, I is a function of time for t greater than 0. And if we look over here, t greater than 0, that means when the switch is turned on. Okay, at t equals 0, that switch is turned on, or it's opened, excuse me. So before it's opened, before t equals 0, this is going to be closed. So we're going to have the way we're going to approach this is we're going to look at the time before it's opened and the time after it's open. So we're going to analyze it from those two different perspectives to look at the current as a function of time. And I'm going to show you two methods to approach this for time less than 0. So I'm going to go ahead and approach it with two different methods just so you can see, and that's not limited to these two different methods, but just to let you know that you can approach this whatever is more comfortable, you're more comfortable using, whichever methodology you're more comfortable using. And a couple other things I want you to notice is this is the circuit that consists of resistors and an inductor, so automatically we know this is an RL and RL circuit. Okay, and we'll see when we look at the time greater than 0, this RL circuit will become, so, and we'll get to that in a second. So when we have t greater than 0, this RL circuit would be a source free RL circuit. Okay, and that's important because then that allows us to use a couple of equations. It allows us to use the time constant tau L over R. Okay, and it allows us to use the current as a function of time equation, where we have the initial current e to the minus t over tau. Okay, so these are a couple things just to keep in the back of our mind when we get to that part there. Let me undo that. Go ahead and highlight this guy and highlight this guy. Okay, just keep that in the back of your mind. Okay, so let's go ahead and we're going to do two methods for t less than 0. Okay, so the first method, so let's redraw this actually. So for t less than 0, our circuit's gonna be, so that means this is connected here. So I'm gonna draw this. The circuit's gonna be this. We have the resistor. We have our current source. And then we have our 12 ohm resistor. Now for this to be closed for a period of time, the inductor here is going to act like a short circuit. So this will be, so when this is closed, the inductor is going to be a short circuit. Alright. And because this is a short circuit, the current essentially is going to be flowing. It's going to avoid this 5 ohm resistor, and it's going to be flowing in this fashion. So because it's going to avoid the 5 ohm resistor, we can get rid of this guy, clip it here and here, and this is essentially gone. It's an open circuit there. So when we redraw this, we can redraw this like this, and now we have 12 ohms here, 8 ohms here. The inductor is gone. We still have our current here as a function of time. We have 15 amps here. This is going to be 24 ohms here. So this is our circuit before we open the switch. Okay, so let's just keep that on the side there. Let's do method 1. Okay, let's do method 1 here. Okay. So method 1, we're going to use the same circuit, and we're going to use nodal analysis, and I'm going to say at this point I'm going to call this node V. I'm going to ground this down here, and then I'm going to say we have our current coming down this way, we have a current coming down this way, and assume our current going down this way, and of course that 15 amps is going up. So method 1, we're going to do KCL at node V, and of course the sum of the currents going in equals the sum of the currents going out. And if we look at the circuit on the left, on the right here, essentially going through node V, we got 15, scroll up a little bit, we have 15 equals V over 24 ohms plus V over 12 ohms plus V over 8 ohms. Okay, and essentially we just need to solve for V here. To get a common denominator, I can multiply the entire thing by 24, and that gives us 360 equals V plus 2V plus 3V, and so that's 6V equals 360, and then V equals 60 volts. Okay, so let's keep that on the side here. So we got our voltage is 60 volts at that node there, and then we want to solve for the current I here, and specifically, so we can say now this I is going to equal to 60 volts over the 12 ohms. There's 12 ohms there, and that's going to give us 5 amps for t less than 0. Now, just like with capacitors, inductors cannot change instantaneously, so t less than 0, you got 5 amps, so at t equals 0, so at t equals 0, you're also going to have 5 amps. Okay, so that's our initial condition there. Alright, and then from there we can solve for the t greater than or equal to 0. T greater than or equal to 0. But before we do that, I want to show you method 2. I want to show you method 2 for t less than 0. Okay. We're going to use the same circuit, except now we're going to define the currents. We still have current coming out to the left here. We still have a current going to the right here. Okay. But now I'm going to give them names. I'm going to say, okay, this is going to be this guy coming in this way. I'm going to call it I sub 1. This guy I'm going to call I sub 2. And of course IT is going to come down this way here. Alright, so how are we going to do this? So I'm going to take that circuit up here, I'm going to rewrite it, I'm going to rearrange it, and then I'm going to take the resistor. We still have our current source, and I'm going to combine the 12 and the 8 ohms that are in parallel. So this is still 24 ohms here, this is 15 amps here, and then at this point 12 ohms in parallel with 8 ohms is going to give us 4.8 ohms. Okay. I'm calling this here I sub 1. Alright, so now we can do a current divider. So I got I sub 1 equals 24 over 24 plus 4.8 times the 15 amps. That's going to give us 12.5 amps. Okay, so it's going to give us 12.5 amps. And then we're going to take this 12.5 amps here and then go back to the original circuit up here and then do another current division analysis. Okay, so what we're going to do now, we're going to define, we have this current up here, we already called it I, we're going to use that again. So now we're going to call, so we got this I1, which is what we just determined to be 12.5. Alright, so we're going to say I is equal to 8 ohms over 8 plus 12 ohms, all that times I1, which is 12.5, and if we solve for that, we're going to get 5 amps. This is our I, and again that's t less than 0, but it's going to be the same thing as I of 0, 5 amps, and in our notation we also call this our big I naught. So the same thing here, we call this our big I naught. Okay, so that's two ways of getting the initial condition for I. Okay, two ways of getting that. So where this guy is 12.5 amps. Alright, so just want you to appreciate and of course there are other ways of solving for this, but there's this methodology. Now let's look at for t greater than 0 or t greater than or equal to 0. So when t is greater than or equal to 0, essentially what we're going to have is a source-free RL circuit, and we're just going to use these two equations. Let's go ahead and write that down here. So if that's the case, we have a source-free RL circuit. I'll draw that here in a second. So that means tau is equal to L over R, and then our I as a function of time is going to be I naught e to the minus t over tau. Alright, and just for the sake of drawing it, because in this case we're going to have to figure out what our R is. We're going to have to figure out what our R is, and we need to get an equivalent circuit. So to do that, we have to come up here and look at the original circuit up on the left here. Look at this original circuit, and then when this switch is open, pretty much the left side of the circuit is gone, and we just have the right side of it. So we only have the right side, so let's go ahead and redraw that. Go ahead and redraw that here. So what we have is 12 ohms here. We have our inductor, which is 2 henries. We have our 5 ohms here. We have 8 ohms here. Connect these guys here. So this is when t is greater than or equal to 0. So what we want to do is we want to get an equivalent resistance here. Okay, get an equivalent resistor. The 12 ohms and the 8 ohms are in series, so we just add those up. we get 20, and when we add those up, 20, then the 20 becomes in parallel with the 5, so we can rewrite this as 20 in parallel with 5, which is going to be our equivalent resistance, and that's going to be 4 ohms. So our circuit's essentially going to be this guy here, 4 ohms, 2 henries. Okay, so it's essentially our RL source VRL circuit, and this 4 is our R equivalent, and then it's a matter of saying, well, tau is equal to L, which is 2 henries, and then over our R equivalent, which is 4 ohms, that's going to give us 1/2. Okay, that's going to give us 1/2, and then we're just going to use the equation I of t is equal to I naught. We said I naught was 5 amps, e to the minus 2t. Okay, and we just plug that in, and that's our equation, and that's our solution here. Okay, so t is 5e to the minus et, and this is in amps. Okay, and this is also known as our current through our inductor. Okay, so that's how you solve this problem with two different methodologies to get the initial condition for the current, and then recognizing that this is an RL source free circuit, we just plug into the equations and we solve for I of t.